Now, see here Ampere circuital law is also can be used to calculate magnetic field. In place of the Barth-Savart law, we can use it here. But see here, we have done already Gauss theorem in electrostatics. In the Gauss theorem also we calculated electric field by assuming here the closed surface around the charge. So, see here we take here a current carrying conductor. Around current carrying conductor we draw a loop, and suppose you have taken small element of the loop here, that is the dl. It is going like this, and magnetic field also at this point is in the same direction. Then the line integral of magnetic field over this closed path in vacuum is equal to mu naught times the current threading the loop. So, according to Ampere circuital law, we can write B dot dl is equal to mu naught I. So, B dot dl, that we can say here, this is the line integral of the magnetic field over the closed path is equal to mu naught times the current current threading the loop. See here, this Amperian loop can be chosen or can be taken in that way, wherever the B is tangential to the loop and you can say a non-zero constant, and also if the B is normal to the loop we can take, and also where the B vanishes. So, all these conditions should be taken for drawing this Amperian loop. So, this loop is actually known as your Amperian loop. So, now by using Ampere circuital law, we will be calculating magnetic field due to solenoid, due to toroid and due to infinitely long conductor. So, now see illustration of Ampere circuital law. We can also say that is the proof of Ampere circuital law, but actually it is the illustration. Suppose you have got a current carrying conductor here, this is I, and now by taking R we can draw here an loop, that is called Amperian loop, and I have taken here a small element dl, and magnetic field is also tangential to this side. So, we can write B dot dl is equal to B dl cos theta, and this theta is equal to 0. So, we can write B dl. Now, B is tangential to this here, and this is infinitely long conductor, current carrying conductor. So, magnetic field due to infinitely long current carrying conductor at a distance r is, we can write mu naught I upon 2, this is 2 pi r. This is the magnetic field due to the straight conductor at point r. Then integration of the dl we can write just 2 pi r, this is along the circumference of this Amperian loop, and this will get cancelled. So, we will be getting here mu naught I. So, we have taken Amperian loop and taken the magnetic field due to infinitely long straight conductor at a point, and then we have integrated over the closed path. So, we have got mu naught I, that is equal to actually Ampere circuital law. So, now let us see applications of Ampere circuital law to calculate magnetic field. So, now see here the magnetic field at a point due to a straight infinite current carrying wire. Suppose you have taken here infinite straight current carrying wire here, carrying current I. We want to calculate magnetic field at a distance r. We take an Amperian loop, and now in Amperian loop we assume here the small element that is dl and also the magnetic field tangential. So, we can write B dot dl is equal to here B dl cos theta, theta is 0. So, we can write B dl. We have to calculate magnetic field at this point. So, B we are going to calculate, and we take this loop such that the B remains constant throughout the loop. So, overall integration is the circumference along the circumference. So, we will be getting B is equal to B into 2 pi r. Now, according to Ampere circuital law, we can write B dot dl is equal to mu naught I. So, now we can take this equation and this equation. So, when we take these two equations, then we can write here B into 2 pi r is equal to mu naught I. So, the B is equal to mu naught I upon 2 pi r. So, this is the magnetic field at a distance r due to infinitely long straight current carrying conductor.